Hi everyone, welcome to this channel once again, and welcome to our series on strength of materials. Kindly subscribe, like, share, leave comments and suggestions at the comment box. Today we are looking at Axial Deformation Statically Indeterminate problem, example 3. Let us quickly look at our question and how to go about it. Good. The composite bar consists of a 25mm diameter A36 steel segment AB with E equals 180 G Pascal and 50mm diameter red brass end segment BA and CB with E equals 120 BP. Determine the reactions at the supports, II, the displacement in A with respect to B. So this is our diagram. Let's see how to go about this question. Good. So when you are given this kind of question, because of the way we have a lot of forces being applied, I suggest that you go with the method of superposition. Don't forget that you have already stated that statically indeterminate problem can be solved using the method of superposition and then the compatibility conditions. But because you have forces, multiple forces in different directions, I am saying that I suggest you use the method of superposition. So let's solve the problem using the method of superposition. First of all, the first thing we need to do is to draw our free body diagram. Draw a free body diagram. Of the structure there. And this is a rigid support, so we can call it FC. This side is also a rigid support. We can call it FD. FD. Then we have 80 at this side. This is 80. This side also is 80. Then we have 120. At this side, we also have 120 at that side. So from this free body diagram, we can say that any force going to the right is negative. Any force going to the right is positive. To the right is positive, and to the left is negative. So from here we can write our equilibrium equation. Fd is going to the left, so negative Fd minus 80. This 80 is also going to the left, minus 80. This 120 is going to the right, plus 120. Plus this 120 is also going to the right, 120, plus FC is going to the right, FC is equal to 0. Then from here, we can say that negative FD plus FC from this expression should be equal to negative 80. Once you have been able to do that from the method of superposition, what you are going to do is that, first of all, you are going to assume that deformations are only caused by the external forces and there is no rigid support at one end. So in this case, let's take it that we are taking the D. We assume that the deformation is only caused by the external forces and there is no rigid support at B. And then in the second instance, you are going to assume that there are no external forces and the deformation is only caused by the rigid support at B. So let's quickly look at that. Our free body diagram for that will look like this. So in the first instance, we are assuming that the deformation is only caused by the external force. and there is no rigid support at D. So we have external forces here. We have our 80. This 80 is also here. We have this side is 120, and then we also have 120. So this is a representation of our free body diagram, assuming that there is no rigid support at this side. Plus, when we assume that the deformation, so the deformation here we call the P, which is as a result of external forces. And we can also assume that there are no external forces, and whatever deformation there is being caused by the reaction, is being caused by the reaction at the support B. Therefore, we can just get a diagram like that, and we don't have any external forces, so the deformation is only caused by the reaction at the side FD. The reaction FD. And the deformation caused by that will be, we can call it delta D. So the total deformation will be dP plus, our total deformation will be dP plus the delta, the D will be equal to 0. Good. So once we have that, it means that when you come to this first session here, you can see that where the external forces is causing the deformation at this side here, you see when you start moving from this point, you encounter a different diameter, so you are going to divide at this section. So this side is going to be number 1. As you move along, you encounter another diameter like that. So this section is going to be number 2, and this section is going to be number 3. So for the external forces, we determine the deformation for section 1, the deformation for section 2, and the deformation for section 3. And for the reaction at D also, you can see that this diameter is number 1. We get it number 2. This side will be number 3. But because there is only one force acting at this side, the deformation at portion 1 and portion 3 is going to be the same. So quickly, let's calculate the deformation as a result of the external forces in portion 1, portion 2, and portion 3. You can see that portion 1, if we cut portion 1 at this side, there's no external force. So it means that there's not going to be any kind of force in portion 1. If we draw the free body diagram for portion 1, we are going to get something like that when we cut at the middle of portion 1. And because there's no external force here, T1 will be equal to 0. And for that matter, the deformation at that side will also be equal to 0. Now, when we pick portion 2, let us draw the free body diagram for that side. So when we pick portion 2, we have the big diameter like this. We have 80 at this side. We also have 80 at that side. And the small diameter is here, which we are cutting into 2. So our reaction here is going to be P2. And P2, we are going to get our deformation. Let's calculate the force P2. We have negative 80 minus 80 plus P2 will be equal to 0. And from there, we can say that P2 in section 2 for the deformation caused by the external force will be equal to 160 kilonewtons. 160 kilonewtons. Then we pick the third section and also cut at the middle. So the third section of free body diagram is going to be like this. Sorry, let me just do it here. The free body diagram, we have the big side like that. We have the small side here. We have the big side like that. And this is going to be our internal force which we are looking for. We have a force of 120. At this side also 120. We have 80 going this way, another 80 going that way. So from there we can say that negative 80 minus 80 plus 120 plus another 120 plus P3 will be equal to 0. And from there we can say that P3 will be equal to 80 kilonewtons. 80 kilonewtons. So once we are done with this, it means that we can calculate the total deformation as a result of the external forces. We can calculate the total deformation as a result of the external forces. So the total deformation as a result of the external forces is going to be section 1 plus section 2 plus section 3. But we have already seen that section 1 will be equal to 0. Therefore, the total deformation as a result of the external forces will be equal to the section 2 plus section 3, which is going to be P2 LAB. AB. P2 LAB over A graph A LAB for section 2 times the modulus of elasticity plus that of P3, and we are, so that is going to be P3 times L3 over, which is from B to C, which is A times our E, modulus of elasticity. And from there, the P should be equal to, we just put in our values, we have 160 for P2 times N exponent 3 times the length of A to B is 0.5. 0.5 over the area, which is 3.142 times 0.025 square over 4 times 180. The modulus of elasticity for that material is 180 gigapascal, which is times 10 to the power 9, plus P3. So P3, we are going to get negative 80 from, sorry, from here it was supposed to be negative 80. Do that correction. It's supposed to be negative 80. So negative 80 times 10 to the power 3 times the length. We are looking at B to C. The length is 0.2 over the area, which is 3.142 times the diameter of that side is 0.5. So we have 0.5 square over 4 times the modulus of elasticity. Sorry for that, let me clean here. Times the modulus of elasticity for that section. And we are told from the question that the modulus of elasticity for that material is 120. 120. So we have 120 times 10 to the power 9. And from there, the total deformation as a result of the external forces is going to be 8. When you do the math, you are going to get 8.374 times 10 to the power -4 meters. So we are done with the deformation as a result of the external force. Now we need to calculate the deformation as a result of the reaction at D. So from there to, we said that you divide into portions 1, 2, 3. But here you can see that because it's a single force here, when we cut in section 1, it will still be equal to P1 when we cut section 3. But the diameter of section 1 and the diameter of section 3 are equal. So we can do them together as one, and then we do two separately and we add them. So from there, the deformation as a result of the reaction at D, we are going to put all the 3 sections together because the force is applied here. But don't forget that we said that you divide according to the diameter. So you have diameter 1, diameter 2, diameter 3. But because 1 and 3 are the same and they have the same force acting on them, we can put them together as 2 into bracket. We can call it, the force in there is going to be FD. P1 will be equal to FD, P2 will be equal to FD, P3 is equal to FD. So we have FD times 2 because of 1 and 3 which we are doing together, and the length is 0.2 over the diameters are the same, 1, 4, 2 times 0.05 square, all on 4 times the modulus of elasticity, which is 120, the same, made of the same material, times 10 to the power 9, plus the section 2, So in the, when you cut through the section 2 also, the P2 is going to be the same as FD. Therefore, we have FD times 0.5 over the diameter, which is 3.142 times the diameter is 0.025. The diameter is 0.025. We have 0.025 square, all on 4 times the modulus of elasticity, which is 180 times 10 to the power 9. Then when you add the 2, as a result of the 3 as a result of the reaction at the support, our d delta is going to be 7.356 times 10 to the power -9 FD. By looking at the directions, you can see that the P will be moving to that side, whilst the deformation as a result of the deflection will be pulling from our free body diagram. It will be pulling our body towards this. So we are going to subtract the deflection as a result of the rigid support from the deflection as a result of the external forces. Good. So allow me to clean all this side now as we calculate for FD. So our total deformation is going to be the deformation. So D as a result of the external force minus D as a result of the reaction at the support from here should be equal to 0. And from there we can see that 374 times 10 to the power -4 minus 7.35 times 10 to the power -9 FD is equal to 0. Then from here, we can say that when you do the math, our FD will be equal to 11.113.8 kilonewtons. Then once you get FD, you put it in our equation 1, which was the equilibrium equation for the whole structure, and then you get FC. You can say that negative, looking at the direction on our free body diagram, you can go back and check. So it's going to be -113.8 kilonewtons because it was pointing to the left. The force was pointing to left, plus FC is equal to -80 from our equation 1, and from there we can get FC equals 33.8 kilonewtons. Then, once you have been able to do that, you come back to the last part of the question, which we were asked to calculate the deflection of AB. Deflection in AB. So let's see how to do that quickly, and with that we can say that we are done with our question. So if we want to get the deflection in AB, we take it from the point B, where we are saying that that is going to be the free end. So we are going to draw our free body diagram again. This is point D. This is a new diameter for AB. And the force in that, we can call it P1. And don't forget that we have forces acting here. This is 80. This is also 80. And then we have our FD, which was pointing this direction. And that is why we made it negative. Don't forget that as we're calculating the main equation. So from here, we can say that we know FD as -113, but because of the direction of the force, it's going to be -113.8 minus 80 minus 80 plus P1 will be equal to 0. Then from there, we can get P1 equals 273.8. Once we get that, we put it in our deformation equation, and we can get the deformation. Because we have gotten the force in AB, we can get the deformation in AB. And the deformation in AB is going to be the force, which is 273.8 times 10 to the power 3 times the length of AB, which is 0.5 over the diameter 3.142 times the diameter, which is 0.025 squared, all over 4 times the modulus of elasticity for that material. And from there, you can see that delta AB should be equal to 1.549 times 10 to the power -3 meters, and we can decide to change it to millimeter. That one is no problem. Good. So we are done solving that question. It was a bit detailed, but I hope we were able to get the concept. However, if there is anybody who doesn't get the concept, you can let us know at the comment section. I will be glad to help you out. Once again, thank you so much for watching. Kindly subscribe, like, share, leave your comments and suggestions at the comment section. Until then, see you next time. Bye-bye.